So in this video we are going to study for reciprocating air compressor. So let's say we have a cylinder here and a piston. Then we have a connecting rod. Connecting rod is connected with the crank. Then this one is called as the bore of the cylinder. This one is called as length of cylinder. We represent D and L. D is called as diameter, L is called as stroke. So Vs is called as swept volume, is given by pi by 4 D square multiplied by L. This is a theoretical displacement. In the PV diagram, the y-axis represents pressure, x-axis represents volume. 1 to 2 we have polytropic compression, 2 to 3 is a delivery, 3 to 4 is polytropic expansion, and 4 to 1 is suction. Normally we assume the index of compression is same as index of expansion. Normally index of compression is given by N1 and index of expansion is given by N2. So it is PV to the power N2 equals to constant. Suction and delivery, the pressure is constant. 4 to 1 represents suction, 1 to 2 represents compression, and 2 to 3 represents delivery. So m dot is called as mass quantity is given by P1 V1 minus V4 upon R2 minus R4. V1 minus V4 is suction volume, N by 60 will convert into meter per kg per second. Number of acting will be single acting or double acting. The other formula for this one is P atmospheric into FAD by 60 upon RT atmospheric. FAD is amount of free air delivered per meter cube per minute. That is why we are divided by 60. This one is called as clearance volume. This one is called as Vs is a stroke volume. And V actual is V1 minus V4. C is defined as the clearance ratio, which is equals to Vc by Vs. Vc is called as clearance volume and Vs is called as stroke volume. Depending upon the value of this, we can define the eta wall, that is the volumetric efficiency based on suction condition, which is V1 minus V4 upon Vs, that is theoretical volume. Now this equation is also equals to 1 plus C minus C into P2 by P1 to the power 1 by N2, where index N2 is index of expansion. So N2 you must take always the index of expansion. If nothing is mentioned, then you take N2 equals to N1 and that ratio will be equal to P2 by P1 to the power 1 by N. Now this equation is used to calculate the dimension of cylinder. Using the mass flow rate we can calculate V1 minus V4 and hence we can calculate Vs, and from Vs we can calculate the stroke or length, whatever it may be required. The delivery temperature at the end of compression is given by T2 by T1 equal to P2 by P1 to the power N minus 1 upon N, where N you can take as the index of compression. Delivery temperature normally asked in number of numericals or is also used to calculate the amount of heat transfer during compression stroke. The indicated power or theoretical power is given by N upon N minus 1 into m dot into RT1 multiplied by the ratio of delivery pressure to suction pressure, that is P2 by P1 to the power N minus 1 upon N. So this power is exactly opposite of our first coefficient, that is N upon N minus 1. So this one is theoretical power, is normally used for the without inside the engine, and the unit is watts. Normally this equation is valid assuming that N1 equals to N2 equals to N. T1 is called as suction temperature, and we can see these coefficients are just exactly opposite of each other or reciprocal of each other. Another equation used is called as Pm into A ln by 60. This equation is commonly used in the case of IC engine to calculate the indicated power or the theoretical power. This one is a power developed for one cylinder, so that is why we have to multiply by number of cylinders if we have more than one cylinder. PM is called as indicate mean effective pressure, and therefore this term is also called as indicate power. Secondly, we have brake power, which is more than in case of engine because the compressor is driven by electric motor, and therefore BP is defined as IP divided by mechanical efficiency, which is the transmission efficiency or mechanical efficiency of the given drive. T1 is normally taken as T atmospheric unless and until mentioned, and P1 is taken as P atmospheric. So these are the default condition in the any numerical if it is not given. The delivery pressure is normally greater than the P2 value, so and if it is not given, then you can take P delivery pressure equals to P2. Similarly, the suction pressure is less than. Let's solve some problems here. We have air compressor delivers air at a constant pressure of 10 bar. It takes air at 1 bar and 15 degrees Celsius. That is the atmospheric condition or suction condition. The index of compression is 1.25, and we want to calculate temperature at the end of compression, work input per kg of air, and the heat transfer during compression. So let's collect the data here. We have the delivery pressure equals to P2 equal to 10 bar, and we have a suction pressure of 1 bar. The suction temperature T1 is 15 degrees Celsius, so 15 plus 273 is 288 Kelvin. Index of compression and expansions are identical, is equals to N equals to 1.25. What we need to calculate is the value of T2, work, specific work, that is a power required by mass flow rate. That answer will be in joules per kg. And finally we want to calculate heat transfer during compression, that is 1 to 2. So we have very first equation is 1 to 2 is polytropic process, and it is known that for polytropic process we can apply a law T2 by T1 equals to P2 by P1 to the power N minus 1 upon N. So substitute this value from the given data and we can calculate the value of T2. So if we substitute, I get T2 equals to approximately equals to 456.4 Kelvin. Now we want to calculate the power. So let's have formula for power first, that is W dot equals to N upon N minus 1 M dot RT1 into bracket P2 by P1 to the power N minus 1. Reciprocal of this term is N minus 1 upon N minus 1. Since we are interested to calculate the specific work, so we divide the entire quantity by M dot. So we get specific work equal to W dot divided by M dot, that is equals to N upon N minus 1 into R into T1 multiplied by P2 by P1 to the power N minus 1 upon N minus 1. Now we can substitute this value. We have to put the R equals to 287, pressure in Pascal, temperature in Kelvin, and index value N is 1.25. So this will be the so if you substitute all this value, we get answer equals to approximately equals to, this is 241.72 kilojoules per kg. Remember, basic answer is joules. I convert into kilojoules per kg by dividing 1000. Finally, we want to find out the heat transfer during compression. So we can apply the first law, Q equals to delta U plus W. Or if I want a specific quantity, I will write lowercase q plus delta U plus lowercase w, indicating specific work. So I have Q equal to delta U is given by CV into T2 minus T1, and W represents the work of compression. That is known to me from the previous value. CV is a gas constant, for air is around 0.718, T2 is known to us is 456.4, T1 is atmospheric condition is 288. So this answer will come in kilojoules. So we only write down 241.72, so we can add kilojoules and kilojoules now. So heat transfer during is given by amount to be 362.6.67 kilojoules per kg. Let's take another numerical. We have a single stage acting, double acting. So let's underline this double acting. Air compressor running at 120 rpm. Power input is 75 kilowatts. And the piston speed is 200 meters per minute. That is correct unit. Suction pressure is 1 bar, delivery pressure is 10 bar, and the volumetric efficiency is 85%. The law follow is PV to the power 1.2 equal to constant. We want to find out the cylinder bore and the clearance volume as a percentage of stroke volume. So let's collect the data here. B and C represents clearance volume, and clearance volume is also given by VC by VS. So we have number of acting 2, IP is 75, twice ln is 200, that is piston speed. P1 suction pressure 1 bar, P2 is delivery, N is 1.25. Volumetric resistance is given by 0.85 is 1 plus C minus C P2 by P1 to the power 1 by N2, but N2 is not known, so we'll take same as index of expansion, that is 1.25. So we can put up this value, and from this we can calculate the value of C, which is come out to be 0.021. It's a percentage of. Now we want to calculate the cylinder bore. For this one we must know the value of Vs first, and the value of Vs we can find out value from V1 minus V4, and V1 minus V4 we can find out from eta wall, and m dot we can calculate from the value of IP of the cylinder. So we have IP, which is equals to the theoretical, is also equals to n upon n minus 1 into m dot into r into T1 into bracket P2 by P1 divided to the power n minus 1 n minus 1 upon n, and whole thing is subtracted 1. Now W dot we know is equals to 75 kilowatts. We are not given the value of T1, so we can assume any value around 300 Kelvin. It doesn't matter what you take, assume the value, it will be automatically cancelled down later on. M dot is basically we can calculate from this value. So you can substitute this data here. R equal to 287 you can take for gas constant. For air we know the value of P2, we know the value of V1, so we can get the value of m dot, which is approximately equals to 0.297 kg per second. This is a very small mass flow rate for the reciprocating compressor. Once we know the value of m dot, we'll try to calculate the value of V1 minus V4, that is the actual capacity. So we will having using equation m dot equal to number of acting, whether single acting or double acting. So this time is double acting, is P1 into V1 minus V4 upon R into T1 multiplied by n by 60, which takes the care of per second. So m dot is 0.297, that you can keep. N is the speed, but we don't know the value of speed, neither we know the value of the stroke also. So what we do is that we'll use the equation eta wall, which is basically defined as V1 minus V4 divided by swept volume or theoretical volume equals to Vs. So we can replace this V1 minus V4 in terms of product of Vs into eta wall, and we'll modify this equation as m dot equals to number of acting multiplied by P1 multiplied by Vs multiplied by eta wall, and rest all terms are same, that is n by 60 divided by RT1. And now we can write this Vs into L. So we can write Vs as equals to pi by 4 d square into L into n. So L into n is known, so we can able to find out the value of d square from this one, and we can put ln equals to what, 200 divided by 2, that is 100 meters per minute. So if you substitute this value, so we can get this value equal to pi by 4 d square multiplied by 100. So let's substitute. For m dot is 0.297, number of acting is 2, P1 is 1 into 10 to the power 5, and gas constant is 287, temperature T1 is 300, and Vs we don't know, so we can write Vs equal to pi, we can substitute for pi by 4 d square. We can even account for ln equal to 100 now divided by 60, and what is left is eta wall. So eta wall is already given to is 0.85. So let's put up this value and solve for d. So we can get the value of d equals to, which will get in meters, is 0.338 meters, that is 33.8 centimeter. The following data refers to a single stage double acting compressor in which air is drawn at 100 kilopascal, which is suction pressure, compressed to 1 megapascal, that equals to 10 bar, and according to the law PV to the power 1.25 equal to constant. The theoretical power is 50 kilowatt, is at 300 rpm, and the piston speed is twice ln, which is equals to 180. We want to find out diameter and stroke of the cylinder. So let's collect data now. So we are double acting, so number of acting equals to 2. Then we have suction pressure P1 equal to 100 kilopascal, that equals to 1 bar. We have delivery pressure equal to 1 megapascal, that equals to 10 bar. So we are collecting data in bar. We have law n equals to 1.25. Index of compression is same as index of expansion. Theoretical power, we also called as IP, is 50 kilowatts at a speed equals to 300 rpm. So capital N equal to 300 rpm. Piston speed is given as twice ln is equals to 180 meters per minute. Now we are knowing the value of n and we are knowing the value of twice ln. So we can substitute for n as 300 and we can calculate stroke in meters. So we get a stroke is equals to approximately 180 divided by 2 divided by 300, that come out to be 0.3 meters. Value of T1 is not given in the numerical, so we again assume equal to 300 Kelvin, that is a very standard condition, and volumetric resistance is not given, so let assume the volumetric is equal to V1 minus V4 divided by Vs equals to 100%. So this was our assumption because the value is required for further calculation. Now because of V1 minus V4 equal to Vs, IP is given by n upon n minus 1 into m dot multiplied by r into T1 into bracket P2 by P1 to the power n minus 1 upon n minus 1. IP is given as 50 kilowatts, n is given as 1.25, and so we can calculate the value of m dot from this data. And P2 you can put up for 10 and P1 you can put up for 1 bar. So we can get the value of m dot. If you substitute, you will get 0.198. Unit is kg per second. Now once we know the m dot, we can write down the formula for m dot, which is equals to number of acting multiplied by P1 into V1 minus V4 upon RT1, which is equals to mass multiplied by n by 60. Since we are assuming eta wall equals to 100%, so V1 minus V4 we can replace as equals to Vs. So we have a equation. So we can put for m dot is m dot equals to n acting multiplied by P1 multiplied by V1 minus V4, which is replaced by Vs, as pi by 4 d square multiplied by L divided by RT1 and multiplied by n by 60. All data is known to us. So the equation 1 and the equation 3, that is IP and m dot, we are using a same T1, that is why it is get cancelled. So we can solve for this and we can get diameter equals to 0.26. A single cylinder double acting. So an acting is 2. Reciprocating compressor has free air delivery of 14. FAD, free air delivery, is 14 meter cube per minute at 1.013 bar and 15 degrees Celsius. So the corresponding pressure and temperature at FAD are basically P atmospheric. So FAD is 14 meter cube per minute, P atmospheric is 1.013 and temperature is 15. Pressure and temperature in the suction or induction is 0.95, that is P1, and this value is 32 is T1. The delivery pressure is 7 bar and index of compression is 1.3. The clearance volume is 5% of sweat volume, that is C is equal to 0.05. The speed of compressor is 600 rpm. We want to calculate the cylinder dimension and delivery temperature and indicate power. So since double acting, so we have 2. FAD is 14 meter cube per minute. The corresponding pressure is P atmospheric is 1.013 bar. The corresponding temperature is 32 degrees Celsius, that is T atmospheric. 15 plus 273 is 288 Kelvin. Suction pressure is P1 is 0.95 bar. Suction temperature is T1 is 32 plus 273, 305 Kelvin. P2 is 7 bar index n1 equal to n2 equal to 1.3 equal to n. Clearance volume C is equals to 0.05 and the compressor speed n is equal to 600 rpm. So to calculate the cylinder dimension, we must know Vs. We want to find out delay temperature, that equals to T2, and indicate power is W dot. We first calculate m dot using the relation of FAD, which is given by P atmospheric multiplied by FAD divided by 60, that is convert from meter cube per minute to meter cube per second, divided by R, the gas constant 287, multiplied by T atmospheric. So we can put for P atmospheric is 1.013 bar, FAD equal to 14 by 60, R is 287 and T atmospheric equal to 288 Kelvin. From this we can find out the value of m dot, which come out to be 0.285 kg per second. Now using the same m dot equation in the terms of V1 minus V4, we can find out the value of V1 minus V4. But before this we'll calculate eta wall, which is equals to V1 minus V4 divided by Vc, and is also given by 1 plus C minus C into P2 by P1 to the power 1 by N2. Since index of compression is same as index of expansion, we'll write 1 by N. So we have C equals to 0.05, P2 is equals to 7 bar, P1 is 0.95 and N is 1.3. So eta wall come out to be 0.817. Now we have another equation of m dot, which is equals to number of acting multiplied by P1 multiplied by V1 minus V4 divided by RT1 multiplied by N by 60. So we can substitute everything from this equation and we can calculate V1 minus V4, which is come out to be 0.013 meter cube per cycle. So in one cycle volume displaced, the actual volume is swept is 0.013. Now since we know the eta wall, so we can calculate the Vs. So Vs equals to V1 minus V4 divided by the volumetric efficiency. So we substitute for 0.013 and 0.817. So we get the swept volume equals to 0.0159 meter cube per cycle, or only meter cube because cycle is not normal written. Now we know that the Vs is equals to pi by 4 d square multiplied by L equals to 0.0159, and if you see the data you will find here that L by D is equals to 1.5. So we can replace L in terms of D as 1.5. So what we get is pi by 4 d square. L is replaced by 1.5 times diameter equal to 0.0159. So this becomes the cube of D, and therefore we can solve for the diameter, and diameter come out to be 0.238 meters, and there hence we can calculate the stroke length, which is equals to 1.5 times the diameter equals to 0.238 multiplied by 1.5 is 0.35 meters. Now we want to calculate the delivery temperature T2. So we have a polytropic compression from 1 to 2, and equation is given by T2 by T1 equals to P2 by P1 to the power N minus 1 upon N. Now we know the value of P1, we know the value of P2, we know the value of T1, so we can substitute all this value. So T2 will get from this data as 483 point something, approximately value is 483 Kelvin, and T1 value you have to put up as 305, not T atmospheric. Take care here. 1 means 1 and T atmospheric means T atmospheric. Finally, indicate power is given by N upon N minus 1 m dot RT1 into P2 by P1 N minus 1 by N minus 1. So by this time you are familiar with this formula. We know the m dot, we know R, that is 287, temperature T1 you have to put up as 305, P2 equals to 7 bar and P1. From this we can get the value of theoretical power, that equals to IP. So that will come out to be 63.29. You can check it, some of plus